Buenos días a todos, bienvenidos. Hoy tenemos con nosotros, como podéis ver, a Eberle. Nos viene del Politécnico de Zúrich y yo, sin querer, pues hice una especie de premonición anticipada de lo que iba a pasar en el partido y le cambié el país para protegerle y puse que era Austria en vez de Suiza. Entonces, estamos en una situación peligrosa porque hoy tenemos un suizo y el lunes que viene un chileno, o sea, no sé lo que va a pasar entre medio. Así que, bueno, hecho esta salvedad, es un joven estudiante, un joven investigador y nos va a hablar pues, de procesos de Pultrusion. Él es ingeniero industrial y seguro va a ser una charla muy amena, interesante, y dejamos el fútbol para esta tarde, que todos tenemos intereses. Así que muchas gracias y cuando quieras.
Okay, buenos días a todos. I appreciate to stay here to present a part of my master thesis. On the other hand, I'd have to apologize, would be in English, but there are some photos inside which should make it much easier to understand. Table of context, I would like to have first like an introduction, then I start with like the process of Pultrusion, then what's composite, then some trials we did for my thesis, then some conclusions, and finally some questions. What's Pultrusion? Pultrusion is actually like a process where we pull like fibers and resin throughout a die, and in this die the product would be curved like this. You can see actually it's very simple. It's like the hand to indicate that we pull like the fiber throughout the die. And finally we get like this kind of profiles. In the industry, like the composite industry, is Pultrusion one of the most fastest rising process, and it's a very high cost effective process. You can see here like the Pultrusion machine. Afterwards, I'm going to explain in detail each of these processes. Actually starts like with the raw material, then passes through like preformer to form like the final shape, then passes through here like the die, where also inside is the resin with the fiber. Then inside the fiber gets curved, as I said, then goes out, and here there's some like a system to get like the process continuous, and finally there's like a saw to cut the profiles. Creels. As you can see here, as it starts, you can like imagine it's like in a sewing machine. You have like here the material which brings to the machine, and actually in the Pultrusion it's like the same. As you can see here, there are three more or less different kind of types how you can order the material. And as you know, it's quite expensive to put the machine in a huge room without being very exact how to put like the material, because like space without using costs quite a lot. Therefore, it's very important to keep it very compact. And you can see on these two pictures how it looks like in the reality, and as well like the size of these creels. The forming guides. We need this from the creels to form the final shape, more or less the final shape to enter the die. And we can see here like two different kinds. Here would be the injection, when I'm going to talk later on, will be here, and here is already pre-impregnated. It means that the material gets here in contact with the resin and forms like the preform. The die. It's more or less shaping the final profile and as well the curve. As you can see here, it's like a normal die, and this picture explains more or less how it works. Here, this different kind of material enter the die, and finally we get like this shape profile. As you can see here how it works, more or less here we have like a little bit impregnated around the fiber, the resin, and the more you get into the die, the more the fiber gets impregnated, And finally, we have the fully impregnated fibers with the resin. It plays as well a very important role, like this tapered enter of the die. The clamping system. As I said, it's like a continuum process. That means the speed has always been the same. Therefore, we need like a system to keep the same speed. There are more or less at the moment two different kind of systems on the market. One works like with some reciprocal clamper puller, which works actually in this way that one is like pulling the fiber, the other one stands here to take over the profile when this is at the end, as you can see here. And the other system, so called the capillary belt. It works like more like with like kind of a belt, which as you can see here turns around and keeps the speed like it continues. And finally, we need as well like a cut-off saw to cut like the pieces in the length. The important thing is that the saw has to be moving at the same speed as the profile, so that we get like a squared and straight cut. So I would like go over once again to summarize what I talked before. We started here with the raw material. Then we can here see like the preformers, and there's some other components to add to improve the process. Then we have here like the die, the clamping system, and finally the cut-off saw. Another important thing is like the production rate. This relates to the thickness of the final profile. I have here a little example with a profile with thickness of 3 mm. You can have more or less 1.2 meter per minute. The pultrusion rate, whereas another profile with the thickness of 90 mm, we have just 200 mm per minute. As you can imagine, that's the speed. It's as well important to get money or to improve the speed. What are the advantages of pultrusion? Advantage is that this is a continuous process, and you can have unlimited length of your product. Or you can even choose during the process what kind of length do you want. Whereas in another system, for example, RTM, where you press, it's like the die is like given with the dimension, so you have to take this and you cannot change. You have a very high fiber volume fraction because about the impregnation compared to other systems. And it's very low cost because it's like a continuum process. You can continue with this process during the night or 7 days, 24 hours. And you have the same quality in the morning as well in the evening, and it's not depend on the person who prepares the material, because it's always the same parameters. But there are as well some disadvantages. For example, you cannot pultrude like a component which has like here's like tapered or even like complex shape, because the die it's like fixed and you pultrude continuous. That means the thickness will be always the same. Furthermore, there are no very high tolerance possible in this process compared to other ones. There are no thin parts, as well for sure no holes. Or after the die you can install like kind of drilling machine, but I think that's a very bad idea so far. When we talk about pultrusion, we talk as well about composites. And when we talk about composites, and normally the people think more about this region, but composites is a very, very, very old material. They've been used this like in the early stage to build like houses with concrete. This is as well like a composite. When you can see here like the polymer, which we're talking about in Pultrusion, how it's like the relative importance in the future. This is as well for me like an important reason why I think Pultrusion will be a very, very important process in the future compared to other materials. What's composite? It's actually very simple. You have like the fibers, or in general material, and you have like a matrix with resin. And together you have like the composite. I took here like a IMDEA composite, which all the fibers aligned in one direction. The normally pultrusion, or the pultrusion starts with like just fibers in one direction. And my project was to use this kind of system, but to put like fibers, which has as well like fibers in the 90 degrees and 0 degrees direction, which makes it a little bit more comfortable. When we talk about pultrusion, we talk about as well about reinforcement. Then we have like two different kind of reinforcement, although it's the same material. We have like the fabrics and textiles, and we have the fibers. You can use actually glass, carbon, amide, and polyester. And with these fibers, we can build different kind of textile. A roving, it's just a simple, just one fiber, as you can see, for example, here. There would be just one roving. Then you have woven roving of fabrics. It looks like this. We are going to use this in our trials, this material, which I have here. I will get given around. There are two different kinds of woven plain roving. As you can see, this is more thin than this one. There's also like an indicate like the area weight. I will give it around. There's also a possibility for triaxial waving, but this does not really work like for pultrusion because you have just this fiber which are aligned in the pulling direction. But you can use this material for other ones or in the future. Then we have multi-axial fabrics. So you have here, that means you have fibers in different angles. Here we have like quadriaxial fabrics. It means you have like fibers in 0, plus 45, minus 45, and 90 degrees. So here prepared, I have here like a biaxial fabric with a higher area weight. Then another biaxial with a lower area weight. Then this triaxial fabric. Everything was with glass, and finally another quadriaxial with carbon. One of the newest will be 3D weaving, where you use like a machine to create your own kind of textile to improve the different kind of forces you have when you apply a force to a composite. You have not only like forces in the 0 direction, but you can have also like in the X direction. And for the future will be that you can produce like a 3D woven which has already the shape of your mold, which finally improves like the preparation time and the quality. And there's as well as some hybrid fabrics. It's like you combine this different kind of material, so here, and you wave this, and you can even improve different material properties. And finally, you have like mats. Normally, you put this above the profile to protect the profile from the environment, from some acids, or improve the surface finish. for the pultrusion, you can use different kind of resins. And to improve the material properties, you can put in some fillers to have a good surface finish. Or for example, if you use this profile like in an airplane, it have to be fire retardant against the high temperatures. To improve the process, you can even add some additives. As I listed here would be an air release, because if you use like the resin, with a simple system, you have some little air inside, and this air will be extended after the pultrusion process, and this air leads that the mechanical properties go a little bit down. And you have as well as some possibility for fiber wetting. That means, as we talked before, you have like the fibers and the matrix, and there you have to be sure that the matrix and the fibers are together, and this is not always the case, and with this you can improve that the resin sticks on the fibers. And you can imagine that the surface tension or the surface energy of a mold with the resin is higher than the resin with the fibers. And we had some problem that the resin stacks inside the mold. And you can see here's like a mold with wood. The problem is that the resin gets sticks here, and once the force of the fibers are not strong enough to pull the profile throughout the die, and finally the profile breaks outside. That means you have to stop the process. As you know, like with polymers, you have like a shrinkage, but that's not a big deal, because if you know like the shrinkage, you can like design the mold a little bit larger to deal with the shrinkage. Finally, would be one of the most important thing about pultrusion is like the viscosity, because the viscosity has an influence how you can like wet the fibers that they get contact with the resin. And as you can see here on this picture, that the viscosity is related with the temperature. A higher temperature indicates less viscosity. And there are also some resin that have very, very, very high viscosity. You cannot deal with this resin without heating up. The advantage of our composites are like the high strength and the low weight. That's the reason why they build like some airplanes with composites. Then like the excellent environment resistance and temperature. Furthermore, to reduce part assembly. And you can good integrate like the composite parts in a structure. Whereas as well like the composite has like some disadvantages, like the poor ductility compared to other materials like metals, and low stiffness compared to traditional combative materials. And finally, the high cost, which I think you could improve, like pulling down the costs with pultrusion, because it's like a continuous process. As I said before, this presentation is a part of my master thesis, and more or less this was like the goal, or like the idea about my master thesis, to figure out or even to set up a system to pultrude with glass or carbon fibers a T-shaped profile with resin transfer molding, like this here. As you can see here, this like from Airbus, you can see the rise in composite structural weight in the airplanes. You can see here like the new 380 with around 30% of composite, whereas the new 350 will be more than 50% of all the weight percentage in composite. what will be the state of art for like the pultrusion, or why do I have to pultruse like this kind of fabric with this system? There's like to know that this one would be like a panel stiffening for an airplane, for a ground plate in the future. And that means it's like a high performance component, and you need like high fiber volume fraction. And finally you have like to bond that with the ground plate. There's like a company in Japan, it's called Jamco. They use like pre-pack. Now we have to discuss what's like a pre-pack. A pre-pack, it's actually the same as I showed before, this plain woven fabric, but the resin is already combined with the fibers. This leads to some problems, that you have high porosity, and that when you pull this, that the fiber are not aligned, because it's very important that the fibers are straight. There are some disadvantages by using pre-pack. For producing the pre-pack, you have to use additional equipment, which costs. Where as well, like the pre-pack has to be stored under cooling condition, whereas as well it's not very economical. If you can see here, that is like the Pultrusion machine, which stands in IMDEA. For my master thesis, I had to modify like the creel, then think about how I can make the injection, and here like the cut-off sublet. It's just more or less the same picture as I showed before, but just the machine in there. What is very important to know when you're doing pultrusion or you start a new process is that you understand where are like the problems, because you cannot like think about cutting the profile without knowing how it works before to cut the profile. That means we have more or less like 5 problems. The first problem is like just to put the fiber into the die, which seems to be very easy, but isn't that easy. And how you deal with this? When you could put like the fibers into the die, then you can a step further, and then you can do like the impregnation or like with the resin. As well, this would be another problem. If you can't impregnate, you cannot produce a part, and you cannot test or improve the whole process. So I mean, you have to improve this or think about how you can deal with this. And here we have the problem 3, which deals like with the impregnation, because the impregnation has a place with the impregnation. You have to know that the impregnation needs to be very good. You need temperature and a high viscosity. And finally, you have like to bring like the profile to the cut-off saw, and then you have to cut it. And you can see like how it works, how you can improve the process, like step by step. What we have, like 2 different dies. One die is like with an open bath, as you can see here. This item here will separate the different fibers to get a better impregnation. I mean, there's as well some advantage of using like this kind of die with an open bath. It's very simple, it's cheap, and it's easy to operate. But there are as well some disadvantages, like you have like from the resin, like the vapor. It's not very good for your health. That means you have to add some fan with a filter. Furthermore, you have a low impregnation because there's no pressure to improve the impregnation. And you have the air bubbles. While you mix in the resin with a mixer, there are little air bubbles inside the resin, and there's no possibility to reduce this. Well, you can add some additives, as I talked before. Then we have like a T-shaped die. This works like with impregnation. Here is like a pressure pot where you mix the resin before, then you feel like the resin inside the pot, and you can see like here it's like a resistance to keep the resin at the same temperature, and then you apply with then you apply here like a pressure, and then the resin moves to the die. As you could see here, here will be like the preform, like the material passing through, and here will be like the injection point where you inject the resin. There are as well some advantages, like you have a closed system, there will be no vapor from the resin, which infects your health. Furthermore, you have a very fast impregnation, whereas in an open bath it's lower. And you have less air bubbles because you work like with pressure. Or you can even decompress the resin before you apply it to the pultrusion. And you have a high productivity because of the speed. But there are some disadvantages, like higher cost for the equipment. Then you have a problem with the backflow, because if you apply like the resin with pressure, the resin tries to flow away, or to flow here out. And you have to think about like the sealing, as we can see here, like a system which prevent that the resin flows here out or inside the mold, because the pressure normally in the normal process is very high. As you can see here, there's like the dimensions of the profile. And actually you can use different kind of textile and materials to produce this. I just show here you can actually use every one of this. On this side, I don't want to talk about this different kind of layups, but I just want to show what's the possibility to set up like the preforms with different kind of materials, with different kind of orders, and then so on. But this actually, as well, like for the future, for our process, will be here some research what will be the best layout. You can imagine that if you use this layout, for example, this profile, and you apply here a force, that would be worse than something like this, we have like a mix. But just like the future work, we have to investigate what will be the best preforms. I just put one of my trials out to explain like we did. For this profile, we used like the plain woven fabrics with some rollers. Then we use this pressure pot with this initial temperature. Then the mold has like 3 different temperature zones to cure it. And here's like the velocity, which is actually very low, and the pressure as well. This profile here was more or less like one of the first ones we produced, and you can see there's no impregnation. I will give it a round. And this one was more or less one of the last one with a much more better impregnation. Here I have another like examples from the flat die, and you can see as well not that good impregnation, because you cannot apply a force to impregnate the fibers. But I have to mention they are like the first trials that we are still improving the process. just wanted to talk about like how do this material looks like in a X-ray. We have like here like a part of the material, and here will be like the pulling direction. As you can see here, that from this side, that here these fibers are more or less straight aligned. Why? If you apply here a force, which is like our pulling force, this fiber get aligned, whereas the other fibers get waved, because this one here or this one here are more or less at the same line. And you can see that this picture shows like before applying a force. And with this picture you can like analyze the material, and you can even see there's like a lack of resin or some air bubbles. Then further you have like to analyze the material, where like the problems about the impregnation, because you have like two kind of impregnation problems or bad impregnations. Like here you can see this like between the different layers or inside the single fibers. And you can do with microscope, you can like analyze like the material to improve your process. And there are as well some additives to improve like the for example like some voids that you, because it's finally here it's missing like the fiber wetting, as I talked before. One very important thing is like the pulling force, because if the pulling force is too high, you cannot pull like the material throughout the die, because there will be break. This pulling force, it's like here you need some little force to pull the fiber from the rolls, then like to compress the fibers, like the share between the die wall, you can see here, and like the fiber bundles before, and the adhesive debonding. This one should be as low as possible, whereas the line speed should be as fast as possible. But the line speed is related to the impregnation, the full polymerization, and finally as well like the cooling. As you can see here, they are like the results. More or less after 6-7 months, we could like produce T-shaped profile and even a flat profile with pultrusion, with all the problems which I'm not going to discuss before, because there are little problems you have to improve, to have to change. What will be the conclusion from my investigations? Pultrusion needs just patience. And more or less the only true method to reach success is like try and error. There are not so many papers available to explain how you can improve, because each die has different shape and a different length, and there are some other problems which occur. If you have like a very shaped die like this, it's get more and more complicated to start with a new process. That means the conclusion would be easier to start with a simple die to know what's going on and then to change. But as you know, another die costs, and between the different dies there are other parameters you have to change. That's a little bit a problem to deal with. And as the shape from the die is already given, and the material you buy as well, you have some problem that the area rate is related to the thickness, and you can until today you cannot like buy so many different kind of fabrics to fix your preform. But as you can see here, we see already light on the end of the tunnel. there are some questions.
Muchas gracias, Rainer. Y tenemos tiempo para algunas cuestiones, así que os animo a preguntar, pero la parte científica, del fútbol aparte.
Pues yo, si queréis,
Sí.
En primer lugar, Rainer, muchas gracias, me ha gustado mucho. La explicación también lo extiendo a todo el equipo, que verdaderamente estéis trabajando y muy bien. Solamente querría apuntar algunas cositas. Una, que el que en una escuela de la categoría de la escuela de caminos se aborden los materiales compuestos es verdaderamente gratificante. Lo digo porque sois prácticamente los únicos, después de los aeronáuticos, en que la razón y ser de que vuelen los aviones, en una gran parte, como muy bien has dicho, es la incorporación de los materiales compuestos. Hay que decir que la pultrusión, dentro del contexto de los composites, cada año aumenta en 2 dígitos. El resto de técnicas de procesado de composites, que no habrá menos de 20 distintas, si no son 30, no suben de los 6-7%. Bueno, pues en pultrusión cada año aumenta. Y aumenta porque se le van cogiendo las aplicaciones. Y no puedo dejar de comentar, aquí a mi lado tengo una doctora ingeniero de caminos que trabaja en el Instituto Laboratorio Oficial Eduardo Torroja, y precisamente conozco el tema muy bien, porque están ensayando redondos en composite, redondos de 60 milímetros, de 40 milímetros, para sustituir en estructuras, si no me equivoco, luego si no, Ana, tú lo corriges, Ana Diego, en pilares a compresión, con resultados magníficos. Estos redondos están hechos en fibra de vidrio unidireccional, con algún que otro truco que yo no puedo explicar, y con resinas vinilesteres, poliésteres, que en principio es suficiente. Que sepáis que esto supone una serie de aplicaciones. El desarrollo lo ha hecho el doctor ingeniero industrial catedrático en elementos continuos, tal, que es Juan Antonio Rovira Soler, que está en Valencia, la Politécnica. Entonces digo esto porque os animo a seguir en esta aplicación, que tiene mucho que ver con los más altos vuelos, puesto que es para lo aeronáutico, porque no es una cosa baladí, es una apuesta, pienso que con muy buen contenido de resultados final. Esa luz del túnel se verá. Y muchas gracias una vez más.
Muchas gracias por el comentario en la parte que nos toca y por las amables palabras. No sé si hay alguna otra pregunta. No, pues lo dejamos por hoy. Muchas gracias.